Will, and I'm like, I'm just joking. I'm just joking. Not really. So that glare is pretty bad. So Vanessa, if you watch this, sorry. This is like completely white from the window, but I like the sun. All right, so I'm trying to teach you something here with the homework. This number tells you what again? Protons. So sodium has 11 protons. How many electrons did we just figure out? 11. That's not a coincidence. Okay? So make sure you listen and pay attention, clear your head, focus. This is really important. Every atom on the periodic table is considered neutral. What does neutral mean? It means it doesn't have a charge. Protons have what charge? Do you guys know? Positive. Positive. Protons are positive. What about electrons? Negative. What's positive 11? Think of simple math. Positive 11 added to negative 11 equal? Zero. So these two add up to 0. So what I'm trying to tell you, which I want you to be clear and focus, pay attention, the atomic number always tells you the protons, and it also tells you the electrons if it's neutral. So if you have a neutral atom, which it is most of the time, it always has the same number of protons and electrons. This is just an example, but I could use any element up there. So let's look at
Magnesium.
Magnesium. How many protons does magnesium have? 12. How many electrons does it have? 12. It's easy. You can add up to 8, 2, right? 2 plus 8 plus 2. That always works. Like, so what Zeke said, add up the electron configuration. That works every time. Or you can just take that number, and that tells you the protons and the electrons. If it's neutral. Go back to the question. Number 2, in a neutral atom. Everything in this room is neutral. Okay, except the electricity in the wall and the ceiling. Okay, if things weren't neutral, every time you touch them, you would get shocked. So like that Tesla coil thing, the zapper there, I'm gonna play around with that again. That's not neutral. That's producing a lot of electrons, so it's negatively charged. So if you grab on that, it's gonna hurt because you're getting charged because you're getting zapped because it has a charge. So most substances at all times are neutral. Okay, you're neutral. Water bottle's neutral, the air's neutral, the desk. So that means the protons and electrons always equal each other. Positives, negatives cancel out. So that's an important concept. We're going to come back to that later in the year, but it's on there, so I'm bringing it up now. So that's how you find protons and electrons. It's the atomic number. Okay. Or again, you can add those up. Okay. Where are we? 3 elements within the same. Are elements with the same outer electronic configuration located in the same period or group? Amanda, what do you think?
Yes.
You said yes?
Yeah.
Okay. Oh. Hey. Oh, no, I think I missed her. Yeah, she's not. Thanks. So, Amanda, let me ask you that again. Same outer electron configuration. Are they in the same period or group?
They're in the same
Group, yes, group. So our elements with really what they're saying is for number 3, are elements with the same valence electrons. That's really what it means. This right here, the outer. Elements with the same outer configuration in the same group or period. If you look at your periodic table and you look at period 3, where sodium is, all right? Sodium ends with 1. What does magnesium end with? 2. And then what does aluminum end with? 3. It keeps going up by 1. So in the same period, they're not the same valence electrons, but in the same group. Everybody in group 1 has 1, 2 has 2. Where is the approximate dividing line? That's the metalloids. I'm not sure how to answer this myself. It's between groups 13 and 17. All right, it kind of zigzags down. I don't know how you guys worded that. I didn't read everybody's answers, I'll be honest. I just looked to see who did it. Anyways, that's what they're looking for. Fluorine, carbon, radon. Kara. Non-metals, good. And where are they?
To the right of the staircase.
Right of the staircase, good. 6. Molly, what do you think?
Metals.
Metals, good. 7. Reagan.
They're metalloids.
Metalloids, right. Boron, silicon, tellurium are metalloids. They're on the staircase. 8. What is the group number of helium, neon, and xenon. Noble. Yeah. What's the number? 18. 9. Nicole.
The atomic number is 3 and a mass is 7.
Yeah. So yeah. Well, what's the symbol for lithium?
Oh,
Li, right? Essentially, it's just asking for the nuclear symbol here. So Li 3, and actually, technically, they want the atomic mass. So yeah, it is 7, but the actual mass is 6.941. So I know it's confusing. Mass number. So the phrase mass number is the atomic mass up there, rounded. So the mass number is 7. The atomic mass is 6.941. I know it sounds crazy to you. You're like, well, it's the same thing. It's a little different. So this is the atomic mass. That's called the mass number. We'll get into that down the road too. Like, what's the difference there? 10. Which have similar outer electronic configurations. I should probably change this one too to say the same. Instead of similar, it should say the same. Emma?
Oxygen and sulfur.
Oxygen and sulfur, yes. Yes, because they're in the same group. Oh, yep. How can you tell? Because they're in the same group. They both end with what, Selma? What? 6. Good. 11. Beryllium, boron, oxygen located in what row or period of the periodic table? Bella. What is it? 2. Yes. And 12. Who has similar properties and how can you tell? I think I call on everybody. Who wants this one? Go ahead, Ray.
I said fluorine, chlorine, and nitrogen and oxygen have similar chemicals properties because they are gases.
Okay, good. They're gases, and what else? What else do they have in common? Fluorine, chlorine, nitrogen, oxygen. Yes, they're all gases. Good job. But are they? What type of element are they? Metal, non-metal, metalloid.
Non-metal.
Non-metal. Good. So that's one answer. I'll take it. Anyone have a different answer? See.
I put fluorine and chlorine because they're in the same group.
Yeah. Fluorine and chlorine, because they're in the same group, they have 7 valence electrons. So, Reagan, what you said is good. I'll take it. The better answer is fluorine and chlorine are in the same group because they have the same number of valence electrons. Those valence electrons are really a big deal. I think I stressed that last week. So that's how we answer that. All right. Let's go to the bookwork here. Go to page 181. Let's go 1 through 7 here. We'll go through that quick. Did you guys, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, good. So you guys all handed that in. All right. I didn't look at that closely yet. So, all right, here we go. Let's go through that quick, and then we'll move on here. All right. So 181. Here we go. So did you guys have downtime, or was it?
Yeah.
Did anyone not have downtime? What did you have? Like 10 minutes left at the end, or something like that?
We were doing it.
Oh, okay, good. That's what I like to hear. All right. Describe the development of modern periodic table. Yeah. Okay. So this is good because you do need to know a little bit of history about it. I don't usually teach it. I usually just give it on this homework. Mendeleev is kind of the father of the periodic table. Lavoisier organized. I'm just going to read the book answer here. Organized a list of the known elements of his day as 4 categories. Let's see, Newlands was the first to organize the elements and show that properties repeat in a periodic way. Mendeleev and Meyer proposed periodic tables showing a relationship between atomic mass and elemental properties. Moseley organized the elements by atomic number instead of atomic mass. So the whole point of that, and I've seen this on the Regents, almost everything having to do with the periodic table or atoms, any research or theories or things that have come out is usually over the course of a long period of time by multiple or many people. Not just one person came up with this. Okay, not just one person's responsible for that. That was the whole point of that. I'm going to skip number 2. that's pretty simple if you just sketch it. Metals, metalloids, nonmetals. Characteristics of metals, nonmetals, and metalloids. This is what we left off with in our notes. We're going to just finish today. I'll go back and we'll zap some things here quick. Let's just say them out loud. What are metals? Metals are strong, malleable, ductile, luster, conduct heat and electricity or energy. Those are the big ones, okay, mostly solids. What about nonmetals? Yeah, the opposite of all that, right? They don't conduct heat or electricity, they're dull, they don't bend, they break, they're brittle, they're softer. They can be liquids and gases, and if they're solids, the solids are usually softer than metals. And then metalloids have properties of both. That's all you really need to say about that. All right, representative element or transition. You probably would have to look that up in the book for that, but the representative elements are like 1, 2, 13 through 18. So lithium representative, platinum is transition, promethium is a transition, I think. Yeah. Where the heck is PM? Down there, 61. And then carbon is representative. Compare for each elements list 2 other elements with similar properties. All right, this was good because of the valence electrons. So iodine, here, let's look over here. So iodine, you could have said any of these. FCl, Br, they all have similar properties because they're in the same group. Barium, you could have said any of these in group 2. And iron, you could have said Ru or Os or Ha, any of those in group 8, right? Those have similar properties to those elements. According to the periodic table, which 2 elements have an atomic mass less than twice their atomic number? So their atomic, this was just kind of like, can you find it? Atomic mass less than twice their atomic number. Well, hydrogen's 1, right? So if you double that, that's 2, so that's less than that. Oxygen, very good. Oxygen, right. Okay. So that's 16, and that's 15.9994, so it's close. All right, and company plans to make an electronic device. They need similar to silicon and lead, but it must have an atomic mass greater than sulfur, less than cadmium. There's only one that it could be. You guys remember the answer? Right, so it's got to be similar to S, so look over here, similar to Si and Pb. It's got to be in this group, okay? But the atomic mass is greater than sulfur, right? So that's 32. So it's got to be bigger than 32, and it's got to be in this group here. Bigger than 32 and less than CD, which is 112. So between 32 and 112, and it's got to be here. It's got to be germanium, right? Ge. And that's it. Okay. Take out your notes. Let's finish up making sure we have all the properties down. We'll go back, zap a couple things, then we're going to move on. All right. We're going to talk about that today. All right. What group's the most reactive metals? Which group? Group 1, most reactive metals. Who's the most reactive non-metal group? Nope, noble gases don't react.
It's the next.
Right, halogens, okay? And that's my next question. The noble gases are inert. They don't react. Why? They are stable. They have a full valence shell. Right. Okay, good. All right, so we just went through all those properties on the homework. Do you guys have all those written down? We already get all that done. I think we did. All right. All right, let's go back and zap a couple things, and then we'll come up and take some more notes. Someone hit the lights on the way back there. No, you should be all right. Just give me 1 second. I forgot to take attendance. Don't play with the Tesla coil.
Totally.
Okay, there we go. Alright, so the whole point of this me too. Stayed up late watching stupid football. Alright. Yeah, they're terrible. I'm about to give up on them again like last year.
We've been on as bad as the bank. 10 from out of there.
Alright, now, remember this thing produces electricity and it goes right through this. What is this? Silicon, so it conducts electricity. It's a metalloid. Metals obviously conduct electricity, right? Notice how the table doesn't conduct very well, but the metals do a better job. Just like playing. Alright, now, non-metal, like a piece of wood, okay? I need a little beaker behind you. Actually, I'll use this crucible.
Did I do the light bulb thing?
No.
Wait, I have a question.
Yeah.
So I broke my hand and I had titanium plates in my hand, but that thing like broke my
That
hand.
would really hurt. That'd be awesome. Yeah. It's not for her. Well, I mean, okay, so hold on. So if I held this to myself, or you, I turned it off, basically. It would hurt, it would shock. You conduct electricity, why? I'm trying to show you only metals and metalloids, watch, non-metals, this piece of wood, doesn't work. Okay, it's not traveling through the wood, all right? So it doesn't work. So how come we can? Are we made of metal? Partly. Water actually doesn't conduct electricity. Be careful with what I said there. So tap water, when it rains, so water outside, tap water conducts electricity, but pure water doesn't conduct electricity. So what's that tell you? There's something else in the water, right? There's it's called ions, metal ions. Metal. So magnesium, iron, and calcium make water hard. We all have hard water, basically, unless you have a water softener. Those conduct electricity. You have all types of ions in your body. What ions are in your body? You better have iron, so that's in your blood. If you don't have iron, then you can't live, because that's the central part of blood. Hemoglobin has Fe+2. So what other ions are in your blood? What does your body need? Think of like minerals and nutrients. Besides iron, what else? When you eat healthy food, what are you putting in your body? Yes, Na+. You do need some of that. What else? Potassium, K+. Good. What else? It's good for your bones. Calcium, Ca+2. You need Mg+2 to help absorb vitamin D, to help the calcium for your bones. You need, there's so many, if we didn't have a Regents at the end of the year, there's an element project I do with my general chem, and you present it to the class, everybody gets an element, you do research. It's cool, I think, because it helps you understand more about why do we need this stuff, where do we get it from, what does it do, but there's a lot of elements in your body and ions. So ions conduct electricity. Tap water has ions. So things like wood, it doesn't have ions. It's non-metal, so it doesn't have the metal or the ions. Metalloids, they do, because they're kind of like both metal and non-metal, and obviously metals conduct really well. Okay? No, I don't want to zap my ear. All right? So the point was the wood does not conduct, right? Non-metals do not conduct. Reagan, hit the middle switch, please. All right, I'm going to show you, actually no, scratch that. Reagan, forget it. I'm going to show you a video of NaCl. of Na and Cl2. So that's still going, right?
Yeah.
Okay. So yeah. So I don't have sodium and chlorine. I put sodium and potassium in water last week. Caught on fire. That was pretty cool because it's violent reaction. Reacts violently. Very reactive. But if you take group 1 and group 17, they're both really reactive. You put them together, it's a very violent reaction, and you can make salt. So group 1 and group 17 do not exist in nature on their own. You can't walk down the road, you can't go through the woods and find fluorine gas or potassium metal just hanging out in a log or something. It doesn't work that way. They don't exist on their own. They are so reactive, they only exist in compounds, like salt, NaCl. So if you want to find sodium and chlorine, you don't find sodium and chlorine, you find sodium chloride, and then you separate to get Na and Cl2. So let me show you this video, because I don't have chlorine, plus it's a lot safer to show you the video. Alright, can you guys get maybe the first 3 lines here? Not today. And sorry. Alright. Oh, I didn't turn this on. Okay. So here's the video. And then we're gonna take a little bit of notes on some random elements on the periodic table, and then that'll be it for the periodic table. What do we have till 10:16?
Yes.
So we'll finish up with that today. So no homework. Come on. Did it not turn on? Come on. So tomorrow we start the first big unit called matter and energy. So, oops. So that's, so they cut a piece of sodium. Again, whoever's doing these things here, they're kind of being little babies about it. They cut a little tiny piece, put it in there. All right. So I think that's the, yeah. So there's the sodium, and then they react. I forget what they're probably putting in hydrochloric acid. I don't know what that is, but it's releasing. See the yellowish, greenish tint? That's chlorine gas. So the gas builds up. Okay, so I don't know, I forgot. That first part I'm a little confused as to what's going on. This is what's, okay, so now, this is filled with chlorine gas. They're heating up sodium, it melts. Now when you heat something up, you give it energy to start reacting, so that's why they're doing that. If you use solid sodium, it doesn't work as well, so they're heating it up. Now watch what happens when it comes in contact with the chlorine gas. Or not.
It's gonna blow up.
Take 3. I mean, it's... Yeah, there we go. So that's what happens. When you get it hot enough and it reacts with the chlorine gas, that's a really, really bright, violent, it's called an exothermic reaction. It's releasing tons of heat. See, that's pretty cool. I think that's cool. I would like to see that in real life, but I don't know. Look at all that crap coming off. Whatever. We don't want to breathe that in anyway.
I have
So,
chlorine.
what's that?
I have chlorine in my house.
You have chlorine gas?
Not chlorine.
You need chlorine gas. You need pure chlorine, Cl2. So that's how salt is made in a lab. All right, so that's pretty cool. I'd just rather show it than do it in real life. And then once it cools down, they take out, and then there you go. There's just a little bit of salt. There's more salt in the container, but that's pure salt. There's this one video that I had that this guy does that reaction, and then he takes the salt out and he eats it. So they take, this is actually pure salt, NaCl, and the guy like puts it on a hard-boiled egg and eats it. I'm like, that's crazy. Because, yeah, I mean, it is salt, but there's probably impurities in there. So anyways, that's how salt's made. So again, the point is, if you add group 1 and group 17, they react very violently, very bright, lots of smoke coming off, and that's where you get that from. All right, so now I'm actually going to leave this like this. So I'm going to give you notes right here because I want to show you something here about carbon. So just a couple things I want to write down here. All right. So first, group 1 and group 17. Let's write down what I said here. Group 1 and group 17 only exist in compounds. Only exist in compounds. An example would be NaCl, right? So NaCl, you're not going to just find them, all right, lying on the ground. They're going to be in a compound. What else? There's just some random, kind of random things I wanted to write down here. Group 1 reacts violently with water. You saw that with H2O. Also, group 1 reacts with acid to make hydrogen gas. That's something you'll see down the road in labs. Make H2 gas. So if you're to pour hydrochloric acid, for example, on sodium or potassium, it would make hydrogen gas. We'll talk more down the road. I thought of it, so I wrote it down. So really, what do you need to know? Group 1's really reactive. You saw the water. I'm just mentioning the acid. We'll get to that. Group 17 we already know is really reactive as well. So that's why they only exist in compounds. Anything else I wanted to say here? You saw iodine sublime. You saw chlorine gas. Okay, we're in good shape here. All right. We're going to take some notes now on just some random elements that I think are pretty important, and that'll be it. How much time do I have? Not much. All right. So let's start with carbon. Where do we find carbon? Coal. Good. Where did coal come from? What? Burnt wood.
That's charcoal.
Yep. And coal is what? Dead plants and animals, right? So carbon is found in all living things, right? Found in all living things. Did you guys know there's like massive amounts of coal in Antarctica, under the ice? So guess what that means? At one time, there was a lot of animals and plants there, right? You guys remember all that neuroscience, right? Remember Pangea? Well, not remember it, but remember learning about it? Anyways, found in all living things. Good. In chemistry, when we say organic, that means carbon. So in real life, there's organic food, and it's a totally different meaning. But in chemistry, when we say organic, we mean it contains carbon. All right, so just keep that in mind. We'll talk more about it down the road. There are 3 allotropes. I'm going to end with this concept here. I'm going to show you pictures. 3 allotropes of carbon. An allotrope, I should probably define that. Same element, but the atoms are arranged differently. So think of Legos. Pick a color.
Red.
Red. Okay. So let's say you have 100 red Lego pieces and all the pieces are identical. So just try and imagine that. And you build a structure out of those 100 Lego pieces. Well, then you take that structure apart, take the same 100 pieces and build some different looking structure. That's what an allotrope is, except it's with elements. So carbon has 3 different shapes, think of it, that it forms. And let me show you the 3 shapes, and then that'll be it for today. Actually, let's list them first. I'll show you tomorrow. Diamond is 1. So 1 is diamond. 2, you're writing with it. Some of you are. Graphite. I think I might have mentioned these already. And then the 3rd one, you'll never get in a million years. Buckminster fullerene,
I could have guessed that.
called buckyball. Buckyball. Buckminster fullerene. So diamond, graphite, and buckyball. You can pack it up, but pay attention up here. See if I can show these to you real quick. Buckyball. Okay, so eyes on the screen, don't go away on me here. Alright, so there's diamond. That's what diamond looks like. So again, the Lego analogy, if you connect all of these are carbon atoms here, these circles, these spheres. If you build a structure that looks like that, that's called diamond. But if you build a structure that looks like that, that's graphite. And if you build a structure that looks like a hollow soccer ball, that's buckyball. So that's buckyball, that's graphite, and that's diamond. So the way these atoms are arranged, again, the Lego analogy works pretty well. You just take the atoms and put them together a different way. And that changes how it looks, and that changes the properties. We'll talk more about that tomorrow. Bell's going to ring real soon. Excuse me, those 2 specific. Someone just hit the lights on the way out. Yeah, I'll do it.